Hello and welcome to PC Retro Tech. In this week's video we're going to be taking another look at MCGA. We've seen it before when I brought out my IBM Model 30. So IBM invented MCGA and put it in their Model 25 and Model 30. It's a kind of proto-VGA adapter. It was used in very few places and in a way it was really just an extension of the CGA adapter. It didn't have any of the EGA modes which later VGA cards would actually support. So anyway, the first order of business was to try and get a nice clear picture for you on camera. And so I thought I would bring out my NEC multi-sync monitor and connect that up. That does give a very nice picture. But unfortunately, as you can see, the cable on this, which is actually hardwired in, has 15 pins. But the output of the IBM Model 30 only has 14 pinholes. One of them is intentionally blocked. And I really didn't want to modify my NEC multisync. It's a very rare old piece of equipment. So I decided to go back to my compact VGA monitor, which I have shown with the Model 30 previously, and it does have a 14-pin connector. And the main problem that I had with this is it was blurry. So the first thing I did was to take the back off the monitor and adjust some of the potentiometers on the neck board there to try and get a better picture out of it. And I think I was actually successful with this. There's still some pin cushion and I wasn't able to find an adjustment anywhere on the main board or on the neck board to change that. But at least the actual image is a lot clearer than it was. I'm not sure that it was actually a focus issue, but at any rate it does look better now. But as you'll see on camera, there's still a problem, and that is that there's a lot of flicker, and this is because of a mismatch between the 70 Hz refresh rate put out by the MCGA adapter and the 60 Hz of my camera. So I looked around for, some kind of update for my camera that might let me do 70 Hz. I actually went through all of my cameras and didn't find anything at all, so it really isn't going to be possible to do anything about that. But don't worry, we won't be using this monitor today. I also thought about trying to get 60 Hz out of MCGA in the MCGA mode, and unfortunately I can't find any information anywhere that would allow me to do that, so I don't think it's possible, or someone can certainly prove me wrong if I am. Today I'm going to be using a very large LCD monitor, which gives a very clear picture. I think it stretches in the horizontal direction a bit, so the aspect ratio won't be perfect, but it is at least a very clear picture. And we're not getting any flicker here, even though it's 70 Hz, because it's LCD. So the only thing that remains now, as you can see, scrolling is really bothersome. I mean, there's this kind of line that runs up the screen. Now I can see that with my eye, it's nothing to do with the camera, and it's because the MCGA doesn't support smooth scrolling. So the first thing I want to look into today is if there's some way that we can do smooth scrolling on the MCGA with some trickery. I'm not really sure, just having a look through the registers that are available, whether that's going to be possible, but I think it's a fun exercise to try anyway. Well, we won't get very far without an image to scroll, so I found this public domain picture of the Grand Teton Mountains online, and I've already converted this over to a VGA palette using the GNU image manipulation program. So I found a set of instructions online for this, and I put a link in the description if you want to make your own VGA pictures this way. Basically you just load a VGA palette file which someone's provided into the GNU image manipulation program, which is free, and then it has options to convert to that palette and to save as a .bmp file. So BMP is a very easy format for us to work with because it normally doesn't have any complicated compression or anything like that. You virtually just read the bytes directly into VGA memory. So unfortunately it looks a little bit blotchy, and that's because I've used a standard VGA palette. You could probably get a better result with a custom palette, but I just don't have time to screw around with that this weekend. The first thing I need to do is to write a program for reading this image from disk into a memory buffer. and unfortunately the one at the link that I talked about doesn't work. It's got some errors in it, and moreover it's not going to work with the 8086 anyway, because this image is 192,000 bytes of image data, and we're not going to be able to do that without far pointers. So I rewrote the program in C, and it'll work with Ball and Turbo C 2.0, and there's a link in the description to my GitHub where you can find that if you want to try it out for yourself. So this image is 3 times the width of the screen, so that we've got something to scroll across. So it's 960 pixels across instead of 320, and of course we'll need to write a program for moving, 1/3 of this image into the video memory at a time. Now I wrote the function for reading the file from disk into memory in C, and it turns out that you can't do this all in one go in Turbo C. We're actually going to have to read it in a small block at a time. In this case I chose to do it 4096 bytes at a time, and so we'll have a small buffer allocated for that, and then we'll copy it from there into a much larger array where we'll reconstitute our image from all of these little pieces. So the file itself contains 2 headers. There's a file header which just gives some basic information like the file type, which should be BMP in this case, the size, and exactly where in the file the image data starts. And then we have our image information header. So this contains information like the width and height of the image in pixels, how many bit planes, bits per pixel, whether it's a compressed image, which it won't be in our case, how many colors are used, that sort of thing. We'll actually ignore all of that since we know exactly what format the data is in. Well, at least I hope I do. And so the function that actually loads a file into memory I've called load BMP, and let me show you that. It's in bmp.c. So this is the function that's going to load the file from disk in chunks of 4096 bytes. We have to have a little function for dealing with far pointers. I'm not going to go into the details here. It's just a slight complication that arises because of the fact that we're on an 8086. The first thing that we do is open the file for reading, and then we check that that all went okay. So there'll be blocks of code like this that check that everything was alright before moving on, and we'll get an error message and we'll quit if something fails. So the next thing we do is read the file header and check that that all went through okay, and now we should be able to see whether we actually have a bitmap file. So if it is, the file type field of the header should contain 4D42, which is the code for a bitmap. And so if it's not a bitmap, we'll exit. Then we read in the image info header, which, as I said, we're just going to ignore, but it's there if we need it. And if that all goes through, then we move to the part of the file where the actual data is for the image itself. And then we're in a position to start reading it in. Now this is where we allocate the 192,000 bytes for our final image after it's all been read in pieces and then reconstituted. So this is where the reconstituted image is going to go. This is where we have to use far pointers because we have more than a single segment, more than 64K of data in the actual image itself. The actual small buffer that we're going to be reading into, the 4096 byte buffer, is allocated here. So this is just an ordinary malloc instead of a far malloc because it's just a very small buffer. And if that all goes through, then we're ready to actually read the file in chunks, and that's what this loop does. So each iteration of this loop will read in 4096 bytes. And this is the read function here, where it's actually doing the reading from the file. And of course, if we're really close to the end of the file, it might not be 4096 bytes, so we have to do a little computation here just to make sure that we don't read over the end of the file on the final read. But anyway, if we've read that many bytes in and that all went through okay, then we can just copy that out of the little buffer into the big array where the final image will be. And so that's what that for loop is for. Now it turns out that there's a little bit of screwing around because you can't really treat really large arrays like normal C arrays in Turbo C, so or at least not in this memory model. Maybe it's possible in other memory models. But we have to screw around a little bit with our far pointers, and that's what that little function at the beginning was for. And I won't go into details, but basically we're just moving our segment around 4096 bytes at a time to make this possible. So that's it basically. That'll read the image into memory. So I already wrote a little program for actually running this, and I called it scroll.c, and I've compiled that down to scroll.exe, and it actually calls that function to read the file in. So let's run that. It doesn't do very much at the moment. It just sits there reading the file in, which actually takes quite a few seconds, and then changes into the video mode. We don't have MCGA on this machine, so it'll have to be run on the IBM Model 30. But then it waits for a key press and goes back to DOS. Now the next thing that I've done is write a little assembly language program for copying the data from our big array into video RAM, and it turns out we can't do all of this in one go either. So even though video RAM is less than 64 kilobytes and MCGA, so it fits in a segment, our big array doesn't, because remember it contains a really ultra wide image, and we only want the left 1/3 of that. And this is 192,000 bytes, so it's not going to fit in a segment. So what I have to do is actually copy it in 4 blocks. And so what I did is I just do 4 blocks of 50 lines each. So a line is 320 bytes or 160 words. And this is the assembly language for really rapidly copying that much data in one go. And once we get to the end of the first line of video RAM, we skip the next 2/3 of the image in the actual array that we're copying from, and then we loop around. So we loop 50 times, and that means 50 lines have been copied across to video memory. Then we have to screw around with our segment in between, and then we copy the next 50 lines over into video memory. And we just repeat this a total of 4 times so that we get a total of 200 lines copied across into video RAM. So that's all very straightforward. So now we're in a position to actually run this on the Model 30 and see what our image looks like. Well, as you can see, we've been partially successful loading this image into video RAM. There is a picture there that's clear, but it appears to be upside down. I mean, who the hell makes an image format with all of the lines in reverse order? That is really weird, so now I have to write some code to change them into the correct order before I load it. But anyway, the other problem here is that it looks very, very pasty, and I don't think there's much I can do about that. That's really just down to the very poor choice of palette. The VGA standard palette really isn't very good, unfortunately, for this image. I'm not going to worry about that too much for now, because I want to get on to doing some scrolling, but first of all we have to get this image up the right way, otherwise it's really just pointless. Well, here's what I came up with to flip our image upside down, and once again, because the image is so large, I have to break it into 4 parts, each of 50 lines. And so basically I set up my segments, and what I'm going to do first is switch the top and the bottom 50 lines of the screen. So there's 50 lines to deal with, and each line will have 960 bytes or 480 words, and here is the actual code for doing the swapping. So it's pretty standard stuff. I just use the AX register as a temporary, and then I exchange the word at the bottom of the screen with AX, and then write AX back out to the word at the top of the screen. So that's all that's required, and then we just loop around 480 times, 480 words per line. Then I just adjust my offsets again for the next pair of lines to swap, and of course I do this 50 times. So that's 50 lines at the top of the screen exchanged with 50 lines at the bottom of the screen. Screw around with the segments in the middle, and then I do the same thing for the middle 50 lines of the screen. So that's all there is to it, and so finally we can actually have a look at our image, hopefully this time up the right way. Well, here's what the image looks like up the correct way. It still looks very pasty in person, but it doesn't actually look too bad on camera, so I think we've been successful with that. So finally we can get on to what the original mission was, and that is to actually scroll the image across the screen. Well, taking a look down this list of MCGA registers, I'm getting a bit excited because they're quite similar to the CGA ones, which I'm really familiar with. This seems to be correct. I found a discussion online, which I've linked in the description, in which they basically seem to confirm that. So we should be able to use the start address registers, which are OCH and ODH there. And what these do on CGA is they take the 2 bytes and they combine them together to make a word, and then multiply that by 2, and that's used as an offset into the video RAM. So in other words, it still reads the same video RAM, but it just shifts where it starts reading from. And so this corresponds to a shift of the picture on the screen. Now basically for every time we increment the start address, we'll get a shift of 2 bytes in that offset. And so that should correspond to a shift of 2 pixels on MCGA, because remember that MCGA has 1 byte per pixel. Now it's not quite that simple to scroll, because obviously there'll be some kind of wraparound. The information that's shifted in on the other side of the screen is going to be read from video RAM somewhere, but we just need to go and fill those locations with new information from our original bitmap image, and then we can actually have scrolling occur. So there's only those 2 pixels going down the side of the screen that we actually have to fill in, and this should be a fairly fast operation, I think. Anyway, to test out whether or not this is going to work at all, I'm going to write a short program which just displays the original image as we already have, waits a short time, like a second or 2, and then changes this start address, and see what the effect is, see if we can see a kind of shift happening. Well, that turned out to be really simple to write. In fact, I think I'm going to get this entire function on one screen. Yep. So the way it works is the registers are at port 3D4H, and so we just need 3D4H in DX. Basically you write the register number to O3D4H and the value to O3D5H. But there's a neat assembly trick to do both at the same time. Instead of doing outDXAL, where AL is the value you want to write, you do outDXAX, and it writes both of the ports one after the other. So in order to make this work, we just need to put the register number in AL, which we do here, and AH has to be the value that we need to write to that register. So OCH is for the high byte of the start address, and so we need the high byte of the start address in AH. And I'm going to pass the start address as a word into this function, and if I put it in AX, then the high byte will already be set correctly. I just need to save the low byte for later, because we need to write that to the other register. And then we just do an outDXAX, and it does everything correctly. So to write the low byte register, we just put the register number in AL. Well, that's just one more than OCH, so we just increment AL to go up to ODH. And then we've already saved the byte that we want to write, so we just move that into AH where it needs to be, and do the same thing, just outDXAX. So it's a really simple piece of code to update this start address. So I also wrote a little program to actually run this. So let me just have a look at that now, because we haven't actually seen this scroll.c file. It's a very short program. So basically I have a little function for setting the video mode, and here is my main program. You can see it's very simple. It's going to load the bitmap file into memory using our load BMP function. It will turn it upside down using the MCGA invert function that we wrote. Then it will change into the MCGA video mode. Then it's going to write the information into the video RAM so that we can see the initial picture. Then it's just going to wait, I think this is 2000 milliseconds or thereabouts, so 2 seconds. And then it's going to change the start address to 1. So in other words, it will change the offset to 2. And then it'll wait for a key and exit. So let's run it and see what happens. Well, let's try this out. If I'm right, this program should load the image onto the screen, and then after a short delay it should shift it, and there's some rubbish should come in on the other side. So let's see, short delay, and it worked. Look at that. And it really hasn't scrolled much at all. It looks like 2 pixels, which is great, exactly what I was hoping. So I think we're going to be able to use this start address to do scrolling. All we have to do is fix up those 2 pixels on the right hand side every time we do a scroll, and I think everything is going to work out just perfect. Well, I have coded something up. It basically waits for vertical retrace to do all the updates, to change the start address and update all of the additional pixels that are being moved onto the screen. But it's unfortunately just not working the way that it should. As you'll see in a moment, there's some weird lines across the image. Now, I don't know what's causing those. It's probably just a silly bug in my code, but unfortunately it's not working the way we'd like. On the other hand, it does look like we're very, very close to having scrolling working in a nice, smooth way. So I'm going to try and update this during the week. I'm totally out of time now. It's actually after midnight already. So if I can get it going, I'll upload a short video with the final result. And if there's really a problem here that's to do with MCGA, which we just don't know about yet, then I'll make a more full analysis of that in the next video. Anyway, either way, this is it for this week. That's all I have time for. Thanks very much for watching. I hope you enjoyed this, and we'll see you in a later video. Bye.